So the topic is how to do loop in functional programming language. So before we talk about a new topic, just want to give you a recap on the principle that we go over last time. So we go over 4 principles in the last sharing section. The first one is that instead of treating the computation of a step-by-step instruction, that we will try to compose them as some mathematic function. And we also, functional programming also prefer or encourage pure function, which is a function that does not have side effect, or given the same input that we would have the same output. And also functional programming is widely used a lot of higher order function, and then they also discourage mutation. So I think the reason why I want to talk about loop is because loop is so common in imperative programming. So you, for example, if you write a for loop, by nature you need to specify a set of imperative instruction, and because functional programming does encourage that paradigm, like it take me some time to get used to like an alternative way to solve the same problem, like where I will use for loop or while loop to solve in imperative programming. And I think because looping itself it's a very simple idea, so I think it's also will be good as provide some easy example to help you understand those principle, which is kind of abstract, that we discussed in the last sharing section. And because all the code example is written in Scala, that I will just talk about a few concepts in Scala. So first is a data type that's commonly used in Scala, which is a list. So list is basically an immutable linked list. And I will assume you guys are familiar with this data type. But the only thing I want to highlight is that the symbol that Scala used to prepend a new element to a list is double colon, which might be very alien to you guys if you didn't program in Haskell or Scheme or something. And another data type that would be used in our code example is called stream. So stream basically is very similar to list, except that it's computed lazily. If you see the API here, basically whatever list has, stream also has it. And the one difference here is that instead of having double colon, when we're trying to prepend an element to a stream, that with pound sign and double colon. And the next slide explain like what do I mean by stream.
Can you go to the previous slide, Jason?
Yes.
What's the line below that, like 0, 1 stream.empty? What's that line?
So this is equivalent to
Initializing.
this one. So basically it's the special syntax where you construct a list. So when you construct a list, you will set 0, the head is 0, and then prepend to this list, and this list is 1, prepend like a no. So no signal this is the end of the list, and this symbol is right associated. So the variation order is Scala would first evaluate the right, and then all the way to the left. And for the stream, then the new is a syntactic sugar for list.empty, but we don't have an equivalent for stream, so we just call stream.empty to construct the stream.
Okay.
So the next slide basically explain what I mean by lazy variation. So assume that we have a function called full, which will return integer 42, and when we call the function, we will generate some side effect, so we know when it was evaluated. If we create a list, which the first element is 0 and the second element is full, then we would see the side effect, like we see some things print to the screen right away. But on the contrast, if we create a stream and we have full as the second element, this time that nothing is printed to the screen. But if we call tel, which will return this part, at this moment that we need to know the value of full, and it's until this moment that this function is evaluated, and then we will see something printed in the screen. So this is very useful when we have a very, very long stream, and then each element might take some time to compute, and then at that point we might not want to not want each element to be evaluated every time. But this is kind of similar to what Spark do for the transformation. Like we do not do any computation until it's absolutely necessary.
Is there anything that can like save the thing like cache similar to Spark? Because in Spark we save in cache because we don't want to recompute the statement every time we use it also.
Yes, this is a good question. So Scala, the stream data type will automatically do that for you. So if we call stream.tel again, then nothing will be printed, and the 42 is cached inside stream.
Oh, I see. Okay.
Is there any other question on this?
No.
So if the function has a side effect, will the cache only store the first value?
Yes, we only store the first value.
Until the action is called, right?
Yes. So basically what stream do is that when it needs the element, it would call the function and assign to a variable. And then after that, it would just reuse that because stream is immutable. So we go to the next slide. So another commonly used concept in a functional programming language, including Scala, is called pattern match. And so it has multiple functionality. So the first one is that you can match a constant, just as the switch case is in Java. You know, in Java there's a keyword called switch, and you can like match a certain value to a constant. So here is an example. So let's say we have an integer called n. Like the syntax is something like match, and then something here. So what this would do is that if n equal to 1, it will map to the string 1. If its n is 2, it would map to this string, and if anything else, it would map to this string. So far, so good?
Yep.
So, but the pattern matching can do more than what the switch case can do. Another commonly used case is that you can unpack some structured data. So for example, let's say we have a tuple. First element is string, and the second element is int. And then in Scala, you can give it alias to anything you want. So here is person. And you can write a function. Says, okay, I'm expecting a parameter called person, and then the type is string. It's a tuple whose first element is string and second element is int. And because we create alias here, I can also replace this with this one, which makes it slightly more readable. And then I would say I want to match person to this structure. And then the order is that Scala will try to match them line by line. So whatever matches first would be used. So let's say that I call this on this tuple, and then we try to match the first one. And because the first string is Martin, it did not match this one, and it will go to this one. And Scala will automatically unpack the value and put Martin to the first variable, and then 58 to the second variable. And then this string is being evaluated. And for this case, it's unpacked to, it matched this one because it's like doing a string comparison, and then it will return the string.
Can't we do that in the switch?
I think if you do it in a switch, then you need to manually unpack the value. So you would say, okay, like in this clause, you would say, okay, the name equal to person, the first element, and then age equal to something. Like I saw people use like work with tuple in like Java or some other imperative programming language, and you need to like need to have two extra lines and unpack the tuple to some other more informative variable name. Does that make sense?
Yes.
So Scala also provide a special data struct called case class. And case class is more or less like struct in other programming language. And just like have the name case class. And what you can do is that like instead of doing something like the tuple is, like every attribute would have a name if you write a case class. And case class can use with the pattern matching. So if you have a variable whose class is person, and whatever attribute you have here, you can unpack the value using the pattern matching here. So the interface is very similar to what we do with tuple, like just we are using the case class person instead of the tuple. Good?
What are like the use cases of this? Like, so if you initiate a class, then like you can call like person.name in say Java or in like Python or something. So what's like the use case of like using pattern matching?
So I think, for example, you might see a lot of person would do what they would do in Java is that they would say if is instant something, and then I would do this, and then if the instant is something else, I will do something else. Right? But that all those operation is doing in runtime, so the compiler cannot help you make sure your type is correct. Like you are basically checking the type of the variable in runtime. But when you're using pattern matching with this particular use cases, the compiler can make sure that all the operation is legal. So for example, you can not only match, so let's say that I have a superclass for person and I have two subclass. And then in the parameter, it's possible that I want to do different thing for two different subclass. And then for that two subclass, the method I can call is different. So when you're using the pattern matching with those two subclass, the compiler can make sure that the class that you're calling, the method you're calling on the class actually exists. And if it does not exist, it will raise exception when you try to compile them. But in Java, if you're using the is instant check, you cannot see the error until you run it.
Okay, got it.
So another use cases for pattern matching is that like usually we used to unpack the list. So you can see list as another special case class. And then when you pass in a list, that you can you will try to see whether this list unpack the list into the head and the tail. And you can also match if the list don't have, like it's an empty list, so it will show exception. So what this method do is try to get the first element of the list. And this is equivalent to this one. So I believe in the last sharing section, Sahan asked a question on like what this is. So basically this like explain, like this is just a syntactic sugar for this case. And what this pattern matching expression do is just trying to get the head of the list. Okay, I think that's all the thing I want to cover for the Scala syntax. So next I will just go over some alternative for like for loop or while loop in imperative programming. All those examples is fairly like easy, so I would not like just like very quickly go over all of them. So let's say the first question that we have is to define a factorial function. You guys are familiar with that? So basically, here's what you would do in an imperative paradigm language like Java or C++. But because Scala is a multi-paradigm programming language, you can also do this in Scala. But usually, if you want to stay pure functional programming, what you would do instead, you would use recursion. So basically, you would do something like that. And this is basically the definition of what the factorial function is. So the benefit of recursion is that it's easy to understand and it's easier to prove its correctness. So just by checking the length of two implementation, like the functional way is much more easy to understand. And the reason why it's easier to prove its correctness is because if we define the factorial function using the functional programming way, we can basically like rewrite them using the substitution rule, like step by step, and then eventually we get this. And this is basically the definition of what the factorial function is. And instead, if we want to check the correctness of the imperative way, we basically need to step through this function and keep track of at each moment what's the value for each variable, which is much more it's still fairly easy for the factorial function, but you can imagine how this would grow fairly complicated if the total number of variables increase. Is there any question on this slide?
No.
So another quick example is how we can find the length of the list. So here we're using the pattern match we just mentioned, and it calculated the length by recursively calling Excel. So if it's nil, that will return 0. If it's like more than, if it's like non-empty list, we basically 1 plus the rest of the list, get rid of the head. But the reason why I include this example is I want to review a performance issue. So because like every time when we have a recursion call, like it would occupy like a stack. So if we have like a very, very large list, that we will have a stack overflow error. So the way how we make sure that does not happen is that when we write recursion, we need to make sure that it's tail recursion. So what tail recursion means is that need to make sure the last expression of the function is the function itself. So if you take a look at the last one, because we are calling 1 plus something, so we need to maintain the position of the function call because we need to return here. So if this recursive happen a lot of time, then we have this error. But instead, if the last call, which is the function itself, then the compiler can help you optimize your program so that you don't need to consume that many stack. But of course, it adds a little bit complexity to the problem, which you need to have you have a local helper function inside, and you need to pass along an accumulator. So it's like there's a slightly more extra work if you want to make sure that your function is satisfy the tail recursion requirement. Any question on this?
So like how does it optimize? When you say it optimizes, it doesn't like create multiple stacks, or like?
Yeah, so the way how I optimize it is that in the previous case, when the function called Excel, it increased the stack level by 1. But because of the tail recursion, when it called Excel, it just drop whatever it has before and then reuse the current stack. Because the new recursive call include all the information you need. You don't need to return to whatever the previous position. That's why it's more efficient.
Okay.
So if you use this the tail recursion to re-implement the length function, then you can see at this time, even though we have like a very large list, it worked this time. So you can also see that even though we can solve that stack overflow problem with tail recursion, but there's a lot of like manual work. Like you need to think about how you can convert that tail recursion, a function that uses recursion to a function that use tail recursion. So it's like a lot of manual work, and you can probably guess those work is pretty much the same across all those functions that use similar approach. So if possible, a better way to do it is to use higher order function. And to be more specific, is those functions that a list on any other iterable would have, like map, filter, reduce, etc. So for example, when we use the higher order function, here's the way that how we will implement for the factorial function. So the fold is basically the same as reduce in Python or inject in Ruby. So basically, it's just like it would initiate the accumulator to 1 and just like keep adding like all the like adding 1, 2, multiple 1, 2, 3, 4, 5 to the accumulator. And is there any question on this slide?
No.
And other common high order functions I mentioned is like map, flat map, filter, and fold. So I think another thing I want to mention is that what's the relationship between, so like high order function and recursion is not something like exclusive. So basically what Scala or the language do for you when they define those high order functions is those high order functions implemented using recursion. So by using higher order function, basically the programming language help you abstract the concept of implementing like recursion. So the example here, in order to keep it simple, I wrote the version that does not use tail recursion, but you get the basic idea like how they implement it. So the actual implementation is different from this because Scala want to implement this, the map, filter, flat map in a way that it can also apply to other collection like stream. And also they the language want to make sure that all those call is tail recursive. But basically this is trying to convey the idea that those high order function is implemented using recursion. So if possible, that we would prefer higher order function instead of you writing the recursion yourself. The same as when you're writing an object-oriented programming language, you would use some higher level method instead of like dealing with memory or like other low-level computation yourself. Okay. So here's just another example that we want to find the longest word in a list. So here's the version that we would use the tail recursion as we discussed in the previous slide. And here's the version that we use higher order function. You can see is much shorter than the one if we implement the recursion ourselves. And this is just another more shorter version as equivalent to this one. Any question on this? Okay.
Hey Jason.
Yes.
Question.
Yes.
In Scala, do you have to define that like the return type? You see like these functions. Oh, is it at the very end? Like a string.
Yes. So return type is optional and sometimes required based on the nature of the function. So most of the time, Scala can guess what the return type is. For example, if you see here that I don't define the type of the variable word because Scala can pretty much guess what's the type based on this assignment. So one common cases that we need to define return type is that when we have a function that recursively calls itself. So for example, like this one, like if you have a function that this function recursively call itself, because the Scala compiler wants to make sure that you are doing the right thing, you would require to write the type, so that it can make sure that when you recursively call yourself, you would not break anything.
That's it.
Also, Sahan, there's no such thing as return void in functional programming language. You can return something.
Return void. So what do you mean?
Like, you know how in Java you can have specified functions as return void, like it has no return?
Yeah.
Yeah, that concept is not exist in functional programming.
Got you. Interesting.
So
Because I'm thinking like even Ruby and Python, like functions always return something. I think Java's like the only language it's like say void. That's what I thought Scala was interesting.
So instead of returning void, what Scala would do is that it returns something called unit, and I'm not sure what that is yet. But basically, if you define a function that does not return anything, it just generates side effect. Now, when you call the function, when you define a function, they will automatically assign this return type. So it's the same as if you, for example, if you type something else, it would complain. But if you put unit, it should pass.
It's
Okay. So here's the last example for the higher order function. Just assume here's the scenario that let's say that we have some sort of data model. And then the model is that we have employee, we have department, we have company. And the association is that a company has many departments, a department has many employee. And the question that we want to answer is that we want to get the name of employee who work at a company with more than $5 million revenue. And also we want to filter the department by, we only want the employee working in the marketing department. So if we use higher order function, what we would do is that we just assume that we have some magic function that will load data from database and give us a list of company. So in order to answer this question, we need to have a very ugly combination of filter and flat map. So basically, I would just like highlight some of them. So like here, like D represent department. So basically, we're calling on department and want to filter by, we're only interested in all those departments whose name is marketing. But you can see the idea is that if you have some complicated problem and you have some like filtering going on, like using higher order function directly is not very readable. And we can try to mitigate this by, let's say, I can extract this whole thing to a separate function to make it slightly more readable. Like here's more readable. But this function is not very useful because it's so tied to the particular problem that we're trying to solve. So if we wrote a function, we want it to be like kind of reusable in other places. So another way to do it is that we can try to flatten it by doing something like this. This is pretty like readable. Like we start from the company, and this will return our company whose revenue is more than $5 million, and we would get a list of all those departments this company has, and then we filter by their name, and we get their employee, and then get the name. So the problem for this is that it generates a lot of intermediate result. Like this, so many, like each of this function call will return something, and like this thing we might not need. So a very extreme scenario is that let's say each company has 1,000 departments. So when you call this, then we actually return 1,000 departments, and then it would stay in the memory. But at the end, we only care about the marketing team. So this way of doing that, even though it's very readable, but it's not very efficient. So far, so good. So the way to solve that is that Scala provide a syntactic sugar to do to solve this kind of problem. So if you find yourself writing some nasty flat map filtering, that you can do something like this. So what this do is that it would you would start with a collection, and then you have this thing, and then they assign each company to this variable C, and then you can do filter, and then you can do you can further operate on this variable, and you can get what you want. So this is so what Scala would do is that if Scala see this this syntax, it will actually convert it to this. So it has the same performance as this, but as readable as this.
no, it's nice.
And this is the most powerful concept that I know. And there's more.
Like writing, like even though writing inefficient like code, you need not even think about how inefficient your query is. There's like Scala automatically executes it at like efficient query.
Yes. And we will not cover about this, but this expression actually has much more use case than just iterate through the collection. So for example, in Scala there's some random number generators, so we can use the same things syntax, but I can replace this as like a integer generator, and then I can point to another integer, and this integer become the actual value of the generator, and then you can like do a lot of things on those. You can do some manipulation given like a random number generator, and they have other data type that can use similar syntax. We can talk about in the next sharing section. So the last section is called lazy variation and infinite list. So like in an imperative programming language, you cannot actually define infinite lists. Like if you declare a list, the list needs to have a finite amount of lengths. But in a functional language, because first it supports lazy variation, you can actually define a list that's infinite. So let's say that the problem is that we want to find the nth prime number. And here is usually how you would do it in imperative language. But I think one of the things this approach reveal is that it's very difficult to get it right. Like you need to like think about, okay, like what should be the initial value for this, and like when you should increase this value, and etc. And another thing is that Scala actually does not have break. So in Python or Ruby, when you're doing a loop, you can use break, and Scala does not break. So you kind of need to have some other way to encounter that. But the general idea is that it's kind of difficult to get it right in an imperative programming language. Is there any question on this slide? Okay. So the first attempt that we can try to solve this problem is that we can use the higher order function. So basically, let's say that we are given a helper function called is prime, and then we can just say, okay, 1 to a large enough number, and then I would filter by is prime, and I would get the nth, so which would answer the question here. But of course, the problem is that, like, how do we know what would be a good value for the upper bound here? So there's 3 scenarios. So one, we are either picking a value that's too small, then we raise exception because there's not that many prime number after we call this function. And the second is that it might be too large. I just write run forever, and it's not very efficient. Like we only want the 50th, and then we like generate a very, very large list because the upper bound is too large. And the ideal case is we want the upper bound to have the perfect value, but the perfect value itself is the answer that we're looking for. So that's like a chicken and egg problem. So the way how we solve it is that we can use an infinite list. And the way that we create infinite lists is we will use a special data type called stream, which we cover at the beginning. Because stream is lazy evaluated, so we can make it infinite. So you can see here that I can define a function, and in a functional programming language, function itself is a data. Like you can see the function take no parameter and just like return a string. And in stream, there's a class method called front. So what this do is that it will create infinite lists from 2 all the way to infinity. So we return 2, 3, 4, all the way to the end. And then we say, okay, I want to filter is prime, and this will return infinite number of prime numbers starting from 2, but you will not evaluate them until we actually access the number. So this will not raise the exception. And then when we want to get the nth prime, we basically just call the prime num and get the nth element.
Question.
Yes.
So the type of the string is int. Do they have an upper limit to the int?
Yes.
So
The upper limit is this. So even though like conceptually it's infinite, but if you are taking a really, really large number, it will still cause the overflow. But just like conceptually, you can define infinite lists. But it's not like overcome. Like if you're getting like the 1 million prime number, like can still cause problem.
So we'll go back to negative numbers.
Yes. Or maybe
like,
or maybe raise
like
ex-
an overflow error.
or maybe raise exception. And we can test this.
Yeah, I mean, it won't raise the exception until you try to evaluate the 2 to the 32 minus
Or then define the
2 to the 32 prime number. I want to say though that if you guys have never seen the proof of the number of prime numbers being infinite, it is a very interesting proof. I would suggest that you look at it.
I think the prime number is like the infinite of infinite. So it's more than infinite.
No, it is not. It's regular. It's countably infinite, and if you prove for the infiniteness of prime numbers, it's very infinite.
I think it's something like I assume there is a very large prime number, and you can prove there is an even larger one.
Yes, it's something along those lines. It's quite interesting.
So I do see a video related to what you said from the TED. It's called the Infinite Hotel Paradox.
Uh,
Oh, that's just proving that the natural numbers are infinite.
I think at the end they use the prime number. You guys can
But
take a
prime
look.
numbers are also countably infinite. They say countably infinite to mean that there is a bijection from the set of numbers to the natural numbers, and that is indeed true.
Got it. Okay, so I think I'm went a little bit over time, so I have two more examples. I think if you guys are interested, you can take a look at the slide. But basically, we'll go to the summary. So in this sharing section, we will cover four approach that can replace the imperative for or while loop, which is recursion, tail recursion, higher order function, and the lazy variation and infinite list. And that will be it.
I hope like the Spark does the automatic like improvement on those queries as well. Spark is written in Scala, right? It should have done it like by itself. Even we write something in Python or like whatever, it should have done the.
I think the Scala library for Spark should probably is much better than other language because it's just like they're written in the same language.
No, I was saying like there was like map filter thing, right?
Oh,
You write map and filter and like that stuff. To write something in Python is like I wish like Spark automatically converted that into most optimized format and done the execution.
I see. I think
Like
uh-huh.
Spark is written in Scala, right?
Yeah, I think if you write if you make the query using the data frame, they can do a lot of things for you. But if you are doing all those map filter using RDD, it's very hard for them to do because RDD is much more unpredictable than data frame.
Yeah, that's
Okay.
So, Jason, to your point earlier, actually,
Yes.
that the short answer is that any subset of a countably infinite set is also countably infinite.
I see. Is there anything called infinite of infinite?
Yes, that's uncountably infinite. Those refer the main example of that one would be real, instead of all real numbers. But to answer your question, anything within order is generally countably infinite, because then you can just, the bijection is order, the first element, second element, third element. If there is an order to it, there is indeed a bijection.
What if you include those like rational number, like pi?
Yes, so the set of real numbers is uncountable.
Okay, real number. Oh, okay, real number include like integer, a flow, like is it irrational number or rational number?
Irrational.
Irrational number, like pi, or some like special like symbol, like the base of log.
That's E.
Yeah.
But yeah, that's the irrational number. Rational numbers are also countable.
Cool.
1/3. The set of all fractions.